Hello everyone, my name is Joshua Powers, and on behalf of my co-authors, I will be presenting today a framework for search and application agnostic interactive evolution. So imagine we wanted to teach a robot to be interesting. We could at first attempt to measure this mathematically, but I think we would find that to be prohibitively difficult, if not impossible. Beyond this, be interesting is also very subjective. Its definition changes from person to person. In the past, human interactive optimization has been used with varying levels of success to solve this type of problem. This is especially true in art and design type problems. However, these methods often fail to take advantage of state-of-the-art optimization, and they don't scale to new optimization methods that may be discovered. This is because the algorithm, task, and interactivity are all designed specifically for and integrated with each other. Thus, we propose a framework to solve such problems by building a framework that is agnostic to the optimization method and the function to be optimized, such that these pieces can be swapped in and out modularly. Let me show you how it works. First, our search method, like in standard optimization, proposes a candidate solution to a surrogate evaluator. Since this is the first solution, it will be placed at the head of a binary tree with value 0. This value is then returned to the search method. Next, another solution, S1, is sent to the surrogate. The surrogate's binary tree has a node at its head already, so a query for human comparison is triggered. An available human evaluator is asked the question, is S1 better than S0 at f, where f could in our case be the function be interesting. And the question then would be, is S1 more interesting than S0? Here the human replies yes. Then S1 is placed to the right of the head node, with the value of its parent node plus 1. This value is then returned to the search method. Next, the method proposes S2. Again, it encounters the head node of the surrogate, triggering a human query. Is S2 better than S0 at f? The human responds no. Thus, the value is placed to the left of the head node, with the value of its parent minus 1. This value is also returned to the search method. Let's do one more. The method proposes S3. The head node is taken, triggering a query. Is S3 better than S0? The human responds yes. The right node is already taken, thus triggering another query. Is S3 better than S1 at f? The human responds no. S3 is placed to the left, and since it is not an edge node, it receives a value equal to the average of its parent and grandparent nodes. Again, the surrogate returns this value to the search method. So optimization proceeds in this manner, filling the binary tree. At each step, we make log n human comparisons, and we receive log n human responses, where n is the current depth of the binary tree. At the end, the best solution will be found at the rightmost node of the binary tree. To test this framework, we decided to simulate human responses rather than use real humans, and we used common, non-subjective benchmark functions that are often used to test optimization methods. We also varied the accuracy of simulated human responses over our test to check its robustness to likely human errors that occur in real life. So to test the effectiveness of our framework, we create a table where each column is represented by one of the 24 non-subjective benchmark functions. Each row is represented by one of the 13 optimization methods. In each of these cells, we compare the fitness achieved under our framework against that of the standard evolutionary setup over n equals 120 trials. We then compare the results with the Welch's t-test and adjust for multiple comparisons. Each cell of the table is filled red if our framework performs significantly worse, blue if there was no significant difference between the two, green if our framework performs significantly better. In the most ideal case, all the cells would be either blue or green. In our results, we found that when the simulated humans responded 100% accurately, our framework actually significantly improved the performance of the methods almost all the time. And in particular, only method 12 seemed to suffer. However, as human accuracy decreases, we start to see many more cells turn red and only a few cells stay green. This is still a positive result since the majority of the cells remain blue. In the future, to really understand how well this works, we would like to test our framework on at least one type of subjective function with real human participants. We feel the current study provides sufficient theoretical motivation to test this framework in such a capacity, and that it provides a good baseline for starting to motivate further research into method and application agnostic frameworks. Source code for this project is available at the GitHub link listed, and please feel free to reach out to me if you have any questions or read the paper if you would like further details. Thank you.